First, I would like to thank the organizers and Basha for another nice conference and a nice day of POD in Cambridge, which we all like, I believe. This is a joint presentation with Tobias, with whom we're working together now at ICON. So it's a joint presentation, but if there are any errors or misprints, I take full responsibility for that. Okay, quick outline. I will introduce nonlinear mixed effect model in population PK/PD, and of course my job is much more easier after Francis' introduction, so I can easily skip some of the slides in my talk. I'll talk just briefly about optimal design and introduce Fisher information metrics, talk about parameter estimation, about different approximations of the information metrics, and then again briefly mention population optimal design software. We don't have to spend too much time now after Francis' talk. And at the end, again, touch upon adaptive designs. So, design of population PK/PD studies. So what we really try to optimize, as you've heard from Franz, the design is a combination of sampling sequences, X, and number of patients on different sequences. So we try to optimize, first of all, those sampling sequences. We try to optimize number of patients on different sampling sequences, and also the number of sampling times within the sequence, because we can take many samples, and the question is how many. Why it is important? Because very often very limited number of samples are allowed to be taken from different patients, especially in special populations for different ethical or physiological reasons. For example, in pediatric populations, it's very often possible to take just 2 or 3 samples, and you have many parameters in the model, so individual estimation simply will not work, so we have to use the population approach. And obviously there are operational issues and there are costs. I won't be talking about costs, but I know that Valery probably will touch upon cost-based design, and the nice thing, there is a way to incorporate costs in the standard optimal design paradigm. Now, what is the standard model for nonlinear mixed effects? So we have population variability and we have measurement variability. So we have 2 sources of variability. So we have parameters, individual parameters gamma of a particular patient, and we usually make assumption about the distribution. It's either normal or log normal. The data, the simplest model, we have nonlinear function, some nonlinear function, and additive measurement error, but we may have also models with proportional error, where variance of your observations depend on the responses. And this is a rather standard model for PK/PD, nonlinear for mixed effect model. And we are interested actually in the estimation of the combined vector of parameters, which are population means, population variance covariance metrics, and variances of the additive error, or also sometimes variance of proportional error. How does typical or particular example of nonlinear function look like? Here is an example of a popular one-compartment model with first-order absorption, and you see that it's a really nonlinear function of unknown parameters. It's the sum of exponential functions. Just one of the simplest examples. Where do we take this? Actually, in compartmental modeling, most of these examples come from systems of differential equations. Sometimes they are linear, but sometimes they are nonlinear, and we have to use the ODE solver for that. So, the key for doing design and for doing estimation is to calculate or approximate the individual information metrics which corresponds to a particular patient. And the design points here are k-dimensional predictors, which are sequences of sampling times. If we know how to calculate the information metrics, everything actually is very simple. We can use standard machinery of optimal design. So we introduce the information metrics in a standard way like this. Then we are usually working with normalized information matrices. We are working not with the numbers, but with the weights, with proportion of patients. We select particular criterion of optimality. We try to minimize it, and minimization is with respect to, in this case, with continuous design, so the weights are allowed to vary continuously, and they have to sum up to 1. And then we have to define the design region, where we can take samples. And this is the design region X, or admissible sampling sequences. The theory heavily relies on the equivalence theorems, go back to Kiefer and Wolfowitz, and then Valery Fedorov, who is here, generalized results for different criteria of optimality. And the equivalence theorem is the basis for the different type of optimization algorithms. We like first-order optimization algorithm. Many people like multiplication algorithms, in particular Tobias, who implemented it in one of the new software tools. But you can find all this in many books published on the subject. I put this slide just for 2 reasons. The first reason is to illustrate that many popular alphabetic design criteria are related to they have nice geometric interpretation. For example, D optimality is the size or volume of the confidence ellipsoid or the confidence region. A optimality, sum of diagonal elements, is related to the sum of the principal axes of the ellipsoid, and E, the minimization of the largest eigenvalue, is also related to the size of the largest axis. And the second reason is that if properly ordered, this abbreviation has a nice relation to the title of our conference of the whole week. Now, so this all I will talk about the design. Now, how to build this important element of design and estimation. And we heard it yesterday from Nancy, who mentioned that both design and estimation problems are heavily or need to know how to calculate Fisher information matrix, and that's the focus of the next few slides. So the simplest model, simplest nonlinear mixed effect model is given here. We can write it in a vector form. So given individual parameter vectors gamma, we have normal distribution with given mean and variance covariance matrix. Now, unfortunately, for nonlinear response function eta, if we try to write down the likelihood for the mean parameters, there is no closed form solution, and even in the case of Gaussian epsilon and Gaussian gamma, you can easily see that having this integral, we cannot really integrate out gammas to get a nice closed form expression. That's why we have to resort to some approximations. And the simplest approximation is to linearize at individual effects gamma, so at some point, which I denote gamma prime. And if you do linearization, you can approximate your observations as linear mixed effect model. So matrix Z here is simply the matrix of partial derivatives of response with respect to unknown parametric gammas. Which gamma prime to take? There are several options. For example, you can take the population mean, or you just take arbitrary guess. And an interesting thing is that depending on the selection of your gamma prime, you get different types of approximation. And this was covered actually by Tobias in his PhD thesis, and then he presented a talk several years ago at PODE. So it may seem kind of strange at the beginning, but it is what it is. So for the nonlinear mixed effect model, we don't have closed form expression. We have to do approximation. Let's think for a second that we have normal distribution. So what happens if we had Gaussian distribution of our random effects? If. And it turns out, in this case, there is a closed form formula for the Fisher information matrix. And it has 2 terms. The first term is standard term, just derivatives of response. And second, the trace term comes from the variability which sits in the variance covariance matrix. And you can find references in some classic books on multivariate statistical analysis. So If you do linearization at the population mean, you essentially will get the formula with both terms. If you do linearization at a guess of parameter, the Fisher information matrix approximation does not have the trace term. And so that's kind of interesting link. Now, if we had normally distributed observations, we could, of course, use maximum likelihood because the expression for the likelihood has a closed form. And under certain regularity conditions and the existence of the limiting matrix, M, we would get asymptotic normality of our estimator. So if you can see here, the limiting matrix M consists of the sum of individual information matrices of your design. And of course, the quality of the estimation depends on the axis, so it will depend on the design. Now, we can use maximum likelihood estimation, just minimizing the likelihood or log likelihood. Or we can use, to do the estimation, some sort of least squares, even for the normal distributions. So when variance covariance matrix does not depend on parameters, we can use something like generalized least squares, and it will be a pretty good estimator. Now, when the matrix depends on theta, it's kind of natural to try to use a simple generalization, plug in this theta here, and do optimization with respect to parameters theta. Unfortunately, this does not work because there are examples when the estimator won't be consistent because you have to fix this parameter theta and use the iterative procedure. And this is what's called iteratively reweighted least squares. So if you look at this formula, it may look a little bit messy, but this term that you try to optimize is very much like this. But you have to fix the value of parameter in the variance and do optimization only with respect to parameters in the response. And the property of this iteratively reweighted least square are quite nice. You get consistency, though the limiting variance covariance matrix will be worse than the limiting variance covariance matrix of maximum likelihood, simply because you won't have the second term in the information matrix. And so these Z are simply, as before, the derivatives of response with respect to unknown parameters. And you get this inequality in terms of ordering of non-negative information, non-negative definite matrices. So there is a way how to improve iteratively reweighted least squares, and for that you really need additional terms in this expression that you try to optimize. And this term is what we called combined iteratively reweighted least square. So this is the same term, but then you have to add another term, which looks quite messy. I didn't even put it there. But the idea is to include square deviations of predicted variance covariance matrix from observed residuals. And you can actually prove that this combined iteratively reweighted least squares is equivalent to the maximum likelihood. So it's just to illustrate that you can use variations of least squares even for normally distributed observations. If you don't have normal distribution, you can still use the same approach, the same type of least squares. You won't get the optimal variance covariance matrix, but the methods will be still consistent and will do a nice job. So again, back to the information matrix. When we started working during our time in GSK, that was probably early 2000s, I had a very simple and maybe simplistic approach to this problem when you try to build optimal design for models where variance depend on unknown parameters. We know that we don't have the normality for our data, but we know about the existence of this magic formula for the normal information matrix for normal vectors. So what if we just use this formula, knowing that it's approximation, do the calculate or approximate information matrix according to this formula, then do design and see how it works in practice. And we worked in many projects with PK/PD modelers in GSK. We had our analytically calculated optimal design. They did simulations, just running Monte Carlo and getting empirical variance-covariance matrices, and they found that comparing to our result that it works pretty well, which was very encouraging for us. One thing to note that even if we want to use this formula, we need to know how to calculate variance-covariance matrix S. And this is actually, again, not very difficult if you use first-order approximation. And this is the formula for the variance-covariance matrix when you have a proportional component of variability. If you don't have proportional, if you have just simple additive errors, this formula, if you look at it, reduces to this. And this is the standard formula for linear mixed effect models. I even use this notation Z, which you often see for the design matrix for random effects. So this is nothing really too new or too complicated. And that's how we started working on doing design for PK/PD models. And at that time, PODE was initiated. And it was, as you already know, in 2006. We had many discussions of population optimal design tools starting in 2007. Franz has already mentioned that, makes my life much easier and saves me a lot of time. And I personally benefited greatly from this discussion because it helped our group in GSK, and then when we continued to improve our software and really to understand better what we have to do and how to do that. And this is the first page of the paper. Which Franz did not have in her slides, and you see all the names. So it was really a product of quite a long discussion and extended in time work, but I think everyone was very happy, and thank you, Franz, for leading this activity. We had two examples, one very simple, one compartment model. Again, you have seen this. And we had when we started the comparison, again, Franz mentioned block structure of of Fisher information matrix. When we started the comparison, we really didn't know the details of what other groups were doing. And then we started, when we found out how the calculations are organized, at the end we got exactly the same results when we got the same assumptions. And it was interesting to see that for this simple one compartment model, when we use the full option, both terms in the information matrix, there was some visible difference for some elements of D. The reduced option, which I would think shouldn't be as good, produced better result when compared with Monte Carlo simulation. And one of the reasons was that we used log normal approximation of individual effects for this model, and with variability not that small, log normal first order approximation for log normal distribution is not very good, as you all know. So there was an example in a paper which was published by Tobias and Reiner in 2010, where they calculated the information matrix explicitly, and they showed that if you use both terms for non-Gaussian data, this leads to substantial overestimation of the information. So you really have to be cautious when using one formula or another and understand which is better. This is the second example, again, example of combined PK/PD model, and these are just plots from the 2015 paper. Unfortunately, they are in black and white. Franz had colored printers, but color plots. But the nice thing, you see that when we use the same assumption, either block diagonal or reduced or full, all software tools produce exactly the same results, which was really a nice outcome of all our discussions and conversations. Now, I mentioned that what we used at the beginning, we used the normal first order approximation, and we used the normal formula as for the normal data. This formula has, you have to know the mean of your vector, and you have to know the variance-covariance matrix. We used first order approximation. The next step to try is what if we estimate the mean and the variance covariance metrics using Monte Carlo, and then plug these values into the formula? And that's what we did. So to do this Monte Carlo for the calculation of the Fisher information matrix, you have to generate many artificial patients according to the standard model, create the mean, create the estimate of the variance covariance matrix, and use these estimators in the formula for the information matrix. Keep in mind that we are still using the normal formula, even though we know that it's not normal. And second is you have to be careful with numerical differentiation. When you do numerical differentiation, the choice of step size is really important. Because, for example, for the combined PK/PD model, it was a system of nonlinear differential equations. There is no closed form. All we can do is to calculate everything numerically, including derivatives. And the choice of step size becomes very, very important. And this is an illustration. When you use a sort of standard step size, we use central differences, say 1/1000. You would think it should work in most of the cases. This red bar corresponds to this regular step size. The blue bars correspond to the estimation from non-mem and monoliths, our benchmark. And you see that the standard selection of standard step size really produces not good results. And you actually have to look at these numerical things more carefully. And the values of step size have to be moderately large. And of course, you may want to use different step sizes for different parameters when calculating the information matrix. Here I want to mention one more thing, that yesterday at Alessandra's talk, she mentioned that you have to be careful when doing simulation. And sometimes it's better before running simulation to think a little bit. Yes, and that is very helpful sometimes, because you can do brute force Monte Carlo and you will end up with some non-very good results. And here is an example how you can do this Monte Carlo here. You can, again, this is the simplest model, one parameter, one response. You have normal distribution of your random effects. You have to select step size for numerical differentiation. So one way, which is a good way, you generate the same values of random variables for the random effects and for measurement error for all step sizes when you do either plus h or minus h. You use the same epsilons and the same thetas. And when you do differentiation, you have to take expected value. You have to find the derivative of the expected value. If you do the simple algebra, you will end up with the sum of individual derivatives. So essentially, you can change the order of integration and differentiation. You can do it in a different way. You can just do brute force Monte Carlo. You can, for different value of h plus or minus, you can generate different thetas and different epsilons. And if you look at this simple algebra, you will end up with something which is very different, and it's really messy. And you have to pay much more attention to the balance between the number of Monte Carlo simulation and step size. And finally, a good approximation should give you nice results for simple examples. And the simple example is the linear mixed model, where you have just parameter times your design point. For this example, the expected values is a linear function. The derivative should be identically x, which is it is with a good approximation. For not so good approximation, you have really a mess. So when L is large, you will probably get rid of artifacts. But this is just an example when you're doing simulation. Just be careful and don't try to run thousands of simulations without any thinking. Approximation options. As I already mentioned, Tobias presented a talk at previous POD, and he considered not just those two. He considered other types of approximations, and some of them were related to calculation of conditional moments. There were links to Laplace approximation, which is often used to estimate parameters in nonlinear mixed effect models, and also for the calculation of information metrics. And there were links to different types of approximation in non-MEM, which is a standard software for the parameter estimation. There was a recent paper by France and Tu Nguyen, approximation of the Fisher information matrix via Gaussian and adaptive Gaussian quadratures. There are still issues about calculation time because it's much more accurate, but still probably can be improved in terms of the running time. And then one thing which I want to mention at the end, all of this population optimal design software mostly are focused on locally optimal design. We have to know the values of parameters. So how to solve this problem or reduce the dependence is the use of adaptive designs, as we know. So what we are doing here, we actually doing estimation and design in stages. And this goes back 50 years ago, statistics paper by Box and Hunter. Many in the room are aware of this paper. So to implement this approach, we need efficient estimation and optimal design tools. And it just happens that in the company we all work now, or many of the people who are in this room, we have both tools. So non-MEM actually belongs to ICONS for almost 10 years. Bob Bauer Group, as you probably know. It's really the pharma industry standard for estimation in population PK/PD model under ICON for almost 10 years. And we have another tool which was developed within this group, the Innovation Center, AdPlan. This is a fully validated software for design, simulation, and analysis of adaptive clinical trials under ICON for about a year. It has some standard toolboxes for confirmatory trials, and it has the new toolbox for dose finding. And Tobias is actually one of the main, if not the main developer of the tool, and he will have a talk later during this conference on Thursday, and you may hear much more about adaptive dose finding tool and about AdPlan. It's based on MCP mod approach, which was adapted by European regulators, and it uses both estimation and optimal design modules. So there is a link between design and estimation already. It doesn't cover the mixed effect models at the moment, but that's the obvious next stage, and that's the plan. So my final comments, again, optimal design becomes more and more popular in pharma industry, as Franz has already mentioned. Adaptive designs are really a combination of design and estimation techniques, and is, as we have seen from, hopefully from these two presentations, both adaptive and optimal design, it's about development of both methodology and software. So the software is coming and becomes more and more available, but still there are many, many open, interesting problems. So there are still a lot of things to be done over the next 10 years, I don't know, 5, 15, 3, or... And so that's it. One thing which I want to mention at the very end. So a little bit of self-advertising in a sense. 2 years ago, we published a book with Valery Fedorov on optimal design. There is a chapter on design for population PK/PD models. And this chapter definitely would be different without the existence of PODE. And because of that, at the preface, I thanked all the members of the PODE community, and specifically Basha and Franz and all software developers for all these nice discussions which we had over the years. So thank you very much.
Thank you. Well, do we have questions? Time is over. I think that, well, Sarah, question. Okay,
I was wondering, actually, I guess it's Tobias's talk from 2012 that I was wondering about. So it was that if you linearize your model not around the individual parameter estimates, but just a guess of the parameter estimates, then you don't have this
Second term. Yes.
But if you guess the mean of the parameter estimates, then you must have that second term,
No,
right?
you don't. If your guess is the mean, you don't.
No,
But
you
if
need
you
to-
realize that the mean, you have. So
I
that's-
don't understand. So if I just guess
Yeah,
the
it was
mean,
not. Yes.
it's still not there.
Yeah.
if you guess the mean, it's still the mean.
No, it's not a mean. If you guess.
No,
Well,
it's
we
more
discussed
about.
that, like,
It's very
I think-
I think it took half 1 hour to discuss that last time. You want to say?
Bye.
I would like to point out at this point one thing which Sergey didn't mention on slide 23, I think it was, is that there are also very nice approximations, for example, from your group, from Joachim, which go back onto not an approximation of the population model for the Fisher information matrix, but what I think is more reasonable to really approximate the individual information matrix. So the individual information matrix, if you would want to approximate this as good as possible, you wouldn't use these population parameter beta at all. You would usually use something like best guess for the individual estimate. You would be closer to the true individual dose response curve. For sure, you don't know this, but that's where Joachim came up with some approximation, the FOCE, I think it was. And a similar one was my PhD, which was just based on the distribution of the individual parameters, which is unknown for sure. So basically what I want to say is best guess or not best guess, first order population model approximation is most surely not the thing to go with.
Yes.
And
I think we should
also your PhD student to Yuan, she did it very nicely with the Gaussian quadrature. That's, I think, the most accurate which we can get, and it's a lot of computation time. That's the problem with these approximations.
Actually, I have one question. Sergey,
Yeah?
Sergey, why we are so concerned about information metrics? Because information metrics is needed basically to define variance-covariance metrics. And if you do all this heavy lifting with Monte Carlo, why not to do it with variance-covariance metrics from the very beginning?
Well, with various covariance metrics, there is a way to do the comparison when you generate the data versus Monte Carlo, but it takes, as Franz showed you in some of the example, it takes days, while all this computation.
You are not moving in the right direction. So, because information metrics basically may not be connected to precision at all. So we believe that asymptotically,
Yeah.
variance-covariance matrix is m minus 1 or whatever. So why not to work with this m minus 1 from the very beginning? So if I knew how to do this, I probably would not ask you this question. So.
Are you talking about the estimation of the variance covariance metrics from the beginning, or trying to get some expression for the information?
Evaluation for this variance, to work from the very beginning in terms of variance covariance method, not information method.
Again, one way which I know how to do this is do Monte Carlo simulating data and getting empirical estimate. I personally don't know the other way, how to calculate this variance covariance metrics
If
directly.
you compare m minus 1 with variance covariance metric, because we say you have nice approximation for information metrics, and what? If it's poor approximation m minus 1, poor approximation of matrix D.
Well, the examples again which we ran for simple models and for more complex models show that some approximations are better than others. Not all of them work always well.
Yeah, that's true.
Well,
Okay.
the devil is in the details, so that's why we need code, right? Okay.
Maximin or Minimax design used quite a bit in PKPD.
I have not seen that much. Again, Franz, if you can comment.
Not a lot, but in the example that I've shown from Novartis, so those response example, which was not a mixed effect model example, this is the design they choose. It was the compromise design was a design which was based on the on the worst case scenario. So yes, they used a kind of min-max design there, but it was model averaging across different shape of models.
Just a quick comment again, not about maximin. Very often you don't use this optimal design per se, because they are locally optimal. You need to know a lot about parameter values. You very often use them as a benchmark. You try to compare the optimal design for different value of parameter combinations with standard design. And if you see that standard design has efficiency of 90%, you probably won't change anything. But if you see that the efficiency drops, it gives you very often a good idea where to move your sampling times. So it's locally optimal design most of the time for now. So there are limitations, but again, if you think about using these as benchmarks, I think that's a more reasonable approach.
Any other comments or questions? Well, thank you very much to both speakers.